Hello friends, welcome to my another lecture on computer algorithms. This is a part 3 of our current lecture series. Currently we are discussing about minimum cost spanning tree, and in part 1 we have discussed about basics of spanning tree. In part 2 we have discussed about the Prim's algorithm, which is another algorithm which can find out the minimum cost spanning tree, and this is the third one, that is Kruskal's algorithm. So friends, before starting I would like to request you, at the end of this particular video, please go to the description section. I provided a test series over there, so you can attempt that test and you can have your knowledge check. So let us move ahead. First of all, let us try to understand what is Kruskal's algorithm. So this is the second possible interpretation of optimization criteria mentioned earlier. So in the last lecture I told you that there can be two ways, and one of the way is the last one, that is the Prim's way, and the second way to find out the particular minimum cost spanning tree is this one, and this is the second possible interpretation for optimization criteria. What is the criteria and all we will discuss. So this interpretation is that the set T, so let us say the set T of edges so far selected for the spanning tree be such that it is possible to complete the T into tree. So what we are going to do is, so let us say for a given graph, let us say a graph has 4 vertices, so we will select the edges in the tree such that the cost of the edges are minimum. Okay, so the smallest cost edge we will select first, the next smallest cost edge we will select next, and we will continue this. If it is happening that an edge, let us say the third smallest cost is selected next, and if the next smallest cost is edge 2, 4, but adding this particular 2, 4 creates a cycle, at the time we are going to ignore this particular edge. So in this way we are going to work, and we are going to take care that there is a possibility that whatever that is currently there, it will later on form a tree. Currently in this case it is not a tree because phi is not yet connected. So tree is always a connected graph. In fact, it will be generally only be forest. Okay, so what we are going to do is, we are going to go on creating the different forests one by one. So in the next slide I will show you the example. So this method is called as the Kruskal's method. So let us consider an example, and then we'll try to understand how does this works. So how does the Kruskal's algorithm work? See, the first step is choose an edge with minimum cost. Okay, so in this case, let us consider all these vertices 1, 6, 5, 4, 3, 2 and 7. So what we will do is, first step is choose an edge with minimum cost. So 1, 6 is an edge which is minimum cost. Okay, then first of all choose an edge with minimum cost, delete it from given graph, and if suppose this is a tree and this is a G, okay, given graph G, and if addition of this edge into T does not form a cycle, add it to T. Otherwise ignore it, otherwise do not add. If it is creating a cycle, then otherwise do not add. First thing is that you have to delete it, and add or not add, it will depend on whether it is creating a cycle or not creating a cycle. Okay, you have added it. So second step is, again delete an edge. The same will be repeated. So choose an edge with minimum cost, delete it from the given graph. First of all, find out which is the second smallest. This is the second smallest. Okay, now here 3, 4. So what we will do is, we will delete it. So 1, 6 is deleted, let us say, and then we will delete 4, 3. We will delete this 4, 3 and we will add it here, because adding this is not creating a cycle. So we will add it. Okay, again we will repeat this. The third, again from the remaining one, find out the edge with minimum cost. So 14 is the smallest one, so 14 will be added over here. Then next smallest is 16. So 16 will delete it from here and we'll add it here. Next smallest is 18. We'll delete it from here, but when I try to add it here, what is happening is it is creating a cycle. So I am not going to add it. So it is otherwise criteria. We are not going to add 4, 7. But we have deleted it from here. Then next smallest is 22, 24, 25 and 28. These are the 4 edges. So smallest is 22. We'll delete it. And what we'll find is 5, 4. We'll add it here. Then next smallest is 24 and 25. We have 2 options. Okay. So next one is 24. We'll delete it from here. But inclusion of this into the tree T will create a cycle over here. So we'll ignore that. We'll ignore adding it to the tree. The next one is 25 and 28. Only 2 are remaining. So 25 is the smallest one and we'll add it here. So how many times we are going to repeat this one is, we are going to repeat it for until n-1 edges are added to T, until n-, so every time we add an edge, at that time we have to count that edge. So total number of edges to be added are n-1 only. Either this condition or another condition is until G is null. So in some condition it may happen that there can be a graph, let us say this graph, which is a disconnected graph. So 1, 2, 3, 4 are connected to each other, but and 5, 6 are connected to each other, but this component is not connected to this component. So for this particular graph, there is no spanning tree possible. There is no spanning tree possible for this. So this Kruskal's algorithm will, if it happens that while creating the spanning tree, it happens that all the edges are deleted for this one. Let us say 10, 12, 13, 4 and 6. So here what will be done? 1, 4 will be added first and that will be deleted from this. This will be deleted. Then next smallest is 6. 5, 6 will be added here and that will be deleted. Then remaining are 10, 12, 13. So 10 will be added. So that is 1 to 2, 10 will be added. And then 2 to 3, 12 will be added. And these 2 are deleted now. So edges, the set of edges, finally 13 is remaining, but adding 13 will create a cycle. We will ignore it. Now all the edges from the given graph G are deleted. That is, graph is null now. If graph is null, it means that the spanning tree is not possible. So either we have to come to the conclusion that check whether the spanning tree is possible or not, and or we have to add n-1 edges. So this is the termination condition for Kruskal's algorithm. Generally, a Kruskal's algorithm, it represents a graph, the contents of the graph in a min heap. So min heap is a special type of a data structure wherein if you delete a given, if you perform a delete operation, what it will do is it will delete a value, it will delete an n, in this case it will delete an edge with minimum cost since it is a minimum heap. So that edge will be deleted and we check whether addition of this forms a cycle. If not, if it does not form a cycle, we will add it to the tree, otherwise we will reject it. So first thing is that the data is represented in a min heap. So T is equal to 5, T is a tree. So initially 5 means there are no edges. In the previous case, we have taken 1, 2, or this graph, let us consider 1 to 2, the cost is 28, then 2 to 3, 3 to 4, 2 to 3 was 12, then 2 to 7 was there, then 7 to 4 was there, then 4 to 5 was there, and 5 to 6 was there, even 5 to 7 was there, and something like this graph previously we have considered. So initially the tree is empty. The tree is empty means these all, so connections are not there. 1 to 2, the connection is not there here. Then 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7. So empty tree is there. It means that there is no edge into this particular graph. So initially T is equal to 5. While T has less than n-1 edges, as I told you previously that we have to add n-1 edges, or set of edges in a given graph is 5. Until any one condition of this becomes false, we have to continue this one. Okay. If any condition of these two becomes false, we have to stop. So then choose an edge VW from E of lowest cost. Then delete UW, that is delete it from E. And then if VW does not create a cycle, then cycle in T, then add VW to T, else discard VW. So deletion is compulsory. Okay, so this is the way in which the particular Kruskal's algorithm works. Moving ahead, this example we have already considered. Okay, in this case, so let us consider the T and E over here is 1 6 or 1 2. Then we have, and the cost of 1 2 is 28. Okay, then we have 2 3. Cost of 2 3 is 16. Similarly, we have 3 4. Cost is 12. Then we have 4 7 with the cost 18. We have 2 7. We have an edge 2 7 with the cost 14. Further, we have an edge from 4 to 5 with the cost 22. We have an edge from 5 to 7 with the cost 24. We have an edge from 5 to 6 with the cost 25, and we have an edge from 1 to 6 with the cost 10. So total we have 1 2 3 4 5 6 7 8 9, maybe more than that, 1 2 3 4 5 6 7 8 9. So total 9 edges are there. So while constructing the tree is initially empty. So tree is initially empty. 1, then 2. So these connections are not there. 3. Empty means there are no edges. 4, 5, 6 and 7. So here first we'll consider an edge 1 6. We'll delete it from here and we'll add it to this. So this is 10. Then next smallest edge is 12. 3 4. We'll delete it from here. So 3 4. We'll add it here. Then next smallest is 2 7. 2 7. We'll delete it from here and we'll add it here. Then next edge is we have 16 is the next smallest. So 2 3 will be added here. So this edge is not connected. I am ignoring this one. The next smallest is 22. 4 5. So 4 5 will be added here. Okay. Even 18 is also there, but that should be ignored because that create a cycle, and finally 5 6 will be added. So this is how the particular algorithm works. So this is the algorithm. We can see here. Now here in the Kruskal algorithm, E is a set of edges, cost is a cost adjacency matrix, N is the number of vertices, and T is a tree. Initially this tree is empty. E is a set of edges in G has n vertices. So cost UV is a cost adjacency matrix. Then T is the set of edges in the minimum cost spanning tree. Construct a heap, minimum heap, okay, and heapify. Then for I is equal to 1 to n, parent is equal to -1. So this care is taken for the purpose of identifying whether the different components are in the different position. For example, in the previous case over here, when 1 and 6 is added, the component number for this is 1. Then 2 and 3 is added, the component number is 2 here. Then 3 and 4 are added, component number is 2. Then 2 and 7 are added, component number is 3. Finally, when we added 2 to 3, the component number 27 is component number for 27 is 3, and for this it is 2. But now what has happened is both are in the same component. So you will make them single component. Now only one component is remaining. Finally, if it happens that I am trying to add 2 vertices which are in the same component, that is 2 is in the component number 2, 4 is in the same component, at that time it is a cycle. So for that purpose this parent and all is done in order to identify each vertex in a different set. We want to keep the vertices in the different sets. Then I is equal to 1, minimum cost is equal to 0. Then minimum heap is not empty, or I is less than equal to n minus 1. So delete and minimum cost edge UV from heap and re-heapify. Then J is equal to find U. So here the same thing is done, which we have already discussed. So this is how the particular Kruskal's algorithm works. Let us consider another example over here and try to apply Kruskal's algorithm to this. So in this particular graph, as we know that there are 8 vertices. So first what we will do is we will make a null graph. Null graph means it consists of only the vertices, not edges. 1 2 7 6 8, then 4, then 5 and 3. 1 2 3 4 5 6 7 8. So over here what we have to do is, in order to apply the Kruskal's algorithm, we have to find out an edge with smallest cost. So this is the edge with smallest cost, that is between 1 to 5. So that will be added here. Next is next smallest is 1 is 6 and 1 is 5. So we can find that 5 is the smallest one. we'll add 5 to it. And adding this, it does not create a cycle. Again, next smallest is this 6. So 2 to 7 is 6. Adding 2 to 7 does not create a cycle. Then next smallest is 7. You can see here. Then 6, 8 does not create a cycle. We'll add it. Then next smallest is 8, and it is 2 to 4. We'll add it because it is not creating a cycle. Then next smallest is 10, and that is from 7 to 4. So if you can see here, so adding 7 to 4 creates a cycle. We'll ignore it. We'll not add it. Then next smallest, there are two next smallest. One is 1 to 2 and one is 7 to 8. So you can select any one of these two. So if I select 1 to 2 first, it does not create a cycle. Now if I select 7 to 8, it creates a cycle. But initially, if you had selected, instead of selecting 1 to 2, you may select 7 to 8, and in that case it will not be creating a cycle. But initially here I have selected 1 to 2, so I am ignoring 7 to 8, but I have to delete it from here. Then total, there are 8 vertices, means 7 edges are to be added currently. So 1, 2, 3, 4, 5, 6 edges have been added. So next smallest is 12, and that is 2, 5. If I add 2 to 5, again it creates a cycle. I am going to ignore it. Then 2, 5 is gone, that is 12, and next is 13. So that is 1 to 3. So 1 to 3 is added. Now since for 8 vertices 7 edges have been added, you can stop here. So this is how the Kruskal algorithm works. If you see the complexity of Kruskal's algorithm, what you can find is over here in the Kruskal's algorithm, choosing an edge with lowest cost. So there is, if you are representing it in a matrix of size n by n, so finding out this one will take n square amount of time, deleting will take 1 amount of time, and if VW does not create a cycle, will take 1 amount of time, and this one is to be done for n minus 1 times. This one is to be done for, that is n square instructions are going to be executed, and this is going to be executed for n times. So this is multiplied by n minus 1. So total complexity of Kruskal's algorithm is n cube. So Kruskal's algorithm grows in terms of n cube. Similarly, in the last lecture I forgot to tell you about the complexity of the Prim's algorithm. So Prim's algorithm also, you can see here that this particular block is going to run for n times, and let j be an index such that near of j is not equal to 0. That is finding out a minimum one. This will again take n square amount of time. So for Kruskal's algorithm as well as for Prim's algorithm, the complexity is big O of n cube. So that's done for this particular Kruskal's algorithm. So now I request you to go to the description section and please attempt the quiz. My next topic will be optimal storages on tapes. Thank you.